Hello and welcome to our lesson on sample size. Today, we'll build on our understanding of probability to explore how larger sample sizes can lead to more accurate estimations. In this lesson, we'll delve into how to use large sample sizes to achieve reliable probability estimates, how to compare the accuracy of different sample sizes, applying this new knowledge to practical examples. Previously, we have established a strong grasp of probability notation by understanding symbols and terms used to discuss probability. We also learnt about set theory and how to manage collections of elements and understand their relationships. And we know about sample spaces, including identifying all possible outcomes of a given experiment. With this foundational knowledge, we can now proceed to understand how increasing the sample size in our experiments helps us make more reliable estimations of probability. For instance, consider the probability of flipping a fair coin and getting heads. If we only flip the coin a few times, our results might be skewed, but if we flip the coin many times, we expect the proportion of heads to get closer to 0.5. This technique is crucial in fields like statistics and data science, where making accurate predictions based on sampled data is essential. Consider a fair coin, where the theoretical probability of getting heads is 0.5 or 50%. If you flip this coin just a few times, say 10 times, you might not get exactly 5 heads and 5 tails. It could end up being 7 heads and 3 tails, which makes it seem like the probability of getting heads is 70%. Or it might be 3 heads and 7 tails, suggesting a probability of 30%. These small samples don't always give a result that matches our theoretical expectation due to the randomness involved. This is where the law of large numbers comes into play. The law of large numbers states that as the number of trials in an experiment increases, the relative frequency of an event gets closer to the theoretical probability of that event. More specifically, if you flip the fair coin many times, say 1,000 times, the proportion of heads will likely be much closer to 0.5 than it was with just 10 flips. Imagine you and your friend each flip the coin for an hour. That's a large number of flips, and you both compile your results. You might find that you get heads approximately 50% of the time, and so does your friend. If you both continue flipping for a day or even a year, your results will converge even further towards the theoretical 50% heads. This happens because the randomness is averaged out over many trials. Now, why is this important? Relative frequencies from small sample sizes can be very misleading. For example, if you based your belief on a coin's fairness on just 10 flips, you could be very wrong. However, with 100, 1,000, or even more flips, your estimate becomes much more reliable. Here's a visual representation. Think of a graph where the x-axis represents the number of coin flips and the y-axis represents the relative frequency of getting heads. At 10 flips, the relative frequency might fluctuate a lot. But as you increase the number of flips to 100, 1,000 or more, the line approaches the horizontal line at 0.5, indicating the true probability. In practical terms, this technique is used across various fields. In statistics, researchers collect large data sets to ensure their results are accurate and reliable. In data science, algorithms are tested on large amounts of data to verify their performance and predictions. Similarly, in quality control processes in manufacturing, taking large samples helps in getting a true picture of the defect rates. To summarize, although small samples can give wildly different results from the theoretical probability, larger samples smooth out the random variations, providing us with reliable estimations. This concept of large sample sizes is fundamental to achieving accurate probability estimates in any experiment or study. In today's lesson, we explored how using large sample sizes can lead to more reliable estimations of probability. We began by considering the example of flipping a fair coin, where the theoretical probability of getting heads is 0.5. Through this example, we saw how small samples might give us misleading results due to randomness, such as getting 70% heads with just 10 flips. However, by applying the law of large numbers, we understood that as the number of trials increases, the relative frequency of an event approaches its theoretical probability. This was illustrated with a graph showing how the relative frequency stabilizes around the true probability as the sample size grows. We discussed why this principle is crucial in various fields like statistics, data science, and quality control, where accurate estimations are essential. By taking large samples, researchers and practitioners can smooth out random variations and achieve reliable results. This technique helps in making sound predictions and informed decisions based on sampled data. To conclude, the lesson emphasized that while small sample sizes can produce erratic results, larger samples provide more accurate and dependable probability estimates. This fundamental concept is vital for anyone conducting experiments or studies where probability plays a role, ensuring that their conclusions are based on solid, reliable data.